The mixed hyperelasticity notebook is in the same place as everything else. Go to UKACM Autumn School. And it's mixed hyperelasticity here. You should have only 2 files, the notebook itself and the parent file. The rest is generated as we go. Can everybody see everything okay, by the way? Yeah, cool.
Yeah, good.
So the notebook starts with theory, beginning Y-mixed formulation, exactly the same as Andre's. Andre created a really nice notebook, so I took his as a skeleton, and I forgot to replace the Poisson equation word here. This is not about Poisson equation, so sorry for the mistake. There are a few bits in the theory which you'll have choices to play with. As Lukáš was explaining during his presentation, we have the definition of rotation, which can be which can have multiple terms. But in the executable we'll be running, you'll have multiple choices. One of them is small rotations. Actually, I'll come back to this one later. Let's run over the notebook first and go there at the end. You'll have multiple choices, starting with the theory. You can slowly go through it if you want to. You don't necessarily have to. I've put some links in later on if you need to know certain things. The problem we'll be looking at is just a simple cantilever beam. And we'll be pulling it upwards. And the fixed is from the right, on the right surface, and we have fixed displacements on the left. And as before, first we import what we need to, including the executables we'll be running. And then we have plenty of predefined equations. If you are interested in them, you can read them. If not, you don't have to. Or what I would advise is when they are being run and you are interested in what's going on, go to them then. Until then, you can just fold them up for the ease of view and move on. Then the cell which you'll spend most time on are the parameters. For the geometry itself, you can change the shape of your box, but the fixed displacements will always be applied on the left and the force on the right, unless you go to the GMesh generation part of the code, which you don't want to at the moment. Whenever you'll be playing with stuff, you can always come back to the cell to pick up the parameters which you'll want to be changing. I assume I've put all of them here. If not, then let me know and I'll fix it for later use. So first of all, we'll generate a mesh. Parameters for that are in these 2 files. First, it creates the parent file. First, it creates the config file, which applies the actual attributes to the block sets of the GMesh generated thing. And then it generates the mesh and applies it. You can see it's a simple box at the moment. And then we've got choice of running 2 different analyses. One of them is a standard formulation, which is quite different from the mixed one. And you just execute it. And the next one is the mixed formulation. If you get too much output, you can just click on the cell itself. Cell, current outputs, toggle scrolling.
Or you can press on the left-hand side of the cell.
This one?
No, below this, below that. Yes, it was highlighted a second ago. Yes, here. Yeah, it's the same.
Good to know. I didn't realize. as we really need. Since it's two different executables, and as Lucas was explaining, we have different modules for different things. These two aren't completely the same and produce different fields as outputs. And also, so here is a little summary of what outputs you can see in each one and play with. And yet again, noticing just before the presentation, in the mixed formulation, we also have det-f and angular momentum fields. If you ever want to see more fields and play with the output files in a nicer way, you can download the VTK file, which will appear here. For example, this one. So let's not have it download. You can just download it and view it in ParaView. So we've got the out so elastic and outstep. Those are the two different ones. But for the ease of the notebook, we can just view them side by side here. The one on the left is the standard formulation, and the one on the right is the exact same problem with the mixed formulation. Viewing the displacements by changing warp field. And in both cases, we are viewing first PLR stress. And for these show fields, you can pick different ones if you're interested. The last one, just for the mixed formulation, shows the error between the displacement in L2 field and the displacement projected to an H1 field. Interestingly enough, you can see that this error is higher where the stresses are higher rather than where the displacements are higher. Across the notebook, you have little comments of what's going on to refer to. Let me know if anything's wrong. I'd like to make the notebook better. Yeah. Then we have a convergence study, which you can learn. What this one does is it takes different orders, different element sizes, regenerates, generates a new mesh for different mesh sizes. Doesn't have to regenerate the mesh for orders. And just runs both of the problems again and again for all of the combinations. Yay. And the results are saved. And then we can plot the results after this thing is done. Since we don't have an analytical solution or any, since we don't have any analytical solution to compare to, we'll be just viewing the global displacements, global norm of the displacements for both of the cases and the PLR stress norm. But for mixed formulation, we can additionally view the global norm of the errors or discrepancies between the displacements in L2 and projected H1 fields. This should be done soon.
And a question for later on. We make a convergence plots. Can we switch on first order for the classical because it's so bad that it's overtake whole because it locks.
Okay.
But not now. But like later on. Yeah. So that what?
So
okay. As you know, probably first order approximation of the displacement with tetrahedrons when you apply the bending of the beam leads to the shear locking, and then the error is so big that it overtakes the whole graph. So then it's better to switch off the first order for the displacements classical because it's very bad. But it works pretty well for the mixed. Mixed never locks.
And since this is running, it's good to point out that what we if we set the order, we set the order for the displacements. And in a mixed formulation, the displacements, let's say if the displacement order is P, the order for stresses needs to be one higher. Okay, this should have been done much faster. Either way, I'll come back to this once it's done. Interesting. So you can play with the different parameters. That's one thing. But also you can have a look at how Cook's beam, so how this would behave with the Cook's beam. I included the file for generating mesh for the Cook's beam. And here you can run it. You can either go back to the functions which we have created before, or alternatively, after you've created the Cook's beam, generated the mesh for the Cook's beam, just don't rerun this function, which creates the box, but run the other two. And the visualization ones. Because the okay. Yeah, because the parameter for the mesh file and subsequently all of the parameter for the mesh file has been changed. So it's going to pick up the last generated mesh you have created. So in this case, it will be Cook's beam. Now I see that the results have come. And as Lukasz was saying, the standard formulation with order one.
See, so it's locked so much that it's underestimate the displacements. First order, that's why it's like overtaking the whole graph.
Yes. And it's a similar story for stresses. So one of the first things you can do, if you want to do convergence analysis, can delete this one and put the 3 in instead, after 2. So just run it for order 2 and 3. And I'm not going to rerun it. That's one of the things you can do. But the best one to see is that when this is just for the mixed formulation. And that's comparing the global error indicator, the global norm of the error indicator, with the element size and the order. Lukasz, do you want to comment on that? I assume you've got much better comments. You are muted.
We solving for a displacement in L2 space. So that's solution that a priori we allow for a jumps in between the elements of the displacements. But we know that the exact solution has to be without the gaps. Yeah, because you cannot create suddenly gaps inside of the material because that will be a crack. So what we see that when we project the L2 space in H1 space, we remove those gaps. And this difference between L2 and H1 tells us about the approximation error. And this is and then we see from the a posteriori, this a posteriori estimate how it should decay. It should decay k+1 when the k is approximation order for displacements. And that dictates those slopes, which you see over here. But even if you go to can you, Adriana, show this plot which you have when it's plot of the error? So then here you can see this error associated with the solution for displacements. And then this error is bigger near the support, and then it's smaller when the displacements are big. Because this has nothing to do with the displacements at the end. It has everything to do with the gradients. And then when you can see the error range is like maximal error is E2 -3 over here. But it will be, I recommend you that as a test, you will go to the third order. You will immediately see that this error drops massively to completely different range. Yeah, so then, and then you can see even that on this plot that you will have errors near to the E2 minus 7, very tiny errors. What is the cool thing over here is that we can very cheaply investigate the calculate the approximation error, even in case when we're dealing with the large deformations, which is not trivial thing when you have to when you're dealing with the nonlinearities, and then you have to a posteriori estimate the error for mesh refinement, because then residual somehow influence your error, and then it's very difficult what is the influence of the error which coming from the Newton method and what is coming from the approximation itself when you have a residual based, for example, error estimators.
Okay. So
Okay,
now for easy run of Crookes beam, you can just run those two cells if you want to have it easy. Run those two cells, you can go back up. Rerun the standard and mixed formulation and all of the viewing things. And you have good thing. Where you can change element sizes and everything else. You might notice also, just to point out, one of the things which Lukasz was saying in his presentation. But at the moment, I'm running mixed formulation with order 1. You can bump it up to order 2. But when the problem is small, you can sometimes notice that the mixed formulation runs slightly slower than the standard one. But when the problems become bigger and bigger, the mixed formulation scales better, catches up, and can overtakes in performance due to the connectivity between the H diff and L2 field.
Yeah, but to add what Adriana is making a point, but we're talking because we assuming that when you run the bigger and bigger problem, you will use more and more CPUs, so you can want to scale it to larger number of CPUs. Adriana, can you show as well this thing with the rotations and stretches?
Yes. So that's the you can find that in the last exercise, which well, this one is probably the more recommended exercise to do, and that's changing the rotations and stretches options. So because it can include, when you click on it, it will take you to the kinematics for rotations, because rotations, you can have small, medium, or large ones. Large rotations take everything into account. Medium ones forget the last term, and the small ones assume that omega, the sin of omega, is approximately the same as omega itself. So you can play with these parameters. As you can see, go to the file with parameters. Here it is. Here I've written the options you have. You can choose between small, medium, and large. And the second thing you can play with is what do you want to have calculated with logarithmic or linear stretches. So linear stretches just don't use the field for logarithmic stretch. All of your element equations just include the stretch itself. When you set it to log, it only uses the logarithm of the stretches and finds, I forgot to change this one as well. This is supposed to be, no, yeah, either way. And it only finds the logarithm of the stretches and gets the stretches afterwards, still in L2.
The importance of this is that you have one code,
Oh,
one source code, which looks exactly the same, but in same time can handle small, moderate, or large rotations, and can run large and small strains formulation. So that is ideal for the testing, because you have one source code which don't have even if loops. It's only adding more or less terms and it's changing the function. So that this is not like 3 versions of the code, it's a 1 version of the code which just simply substitute different kinds of the functions at the end. And then that is linked as well to the robustness, because then engineer or stress analysis which run the analysis can investigate effect of the different features which one implementation it's a tool which can be exploited. And then if he, for example, recognize that he don't want to include the large rotations because it's not important for his loading case, he can exploit that, because then he will have a faster convergence, and so on and so on. So it's a nice tool, and this is like one of the like add-ons to the, which is like additional feature of the mixed elements. Not the key one, but additional, which this beauty of the flexibility of switching nonlinearities and switching them on, because everything is separated. You have a separation of the nonlinearities. And even we don't test that, but this is for a future, someone can exploit like a fishing expedition, that what will happen, for example, if you will assume that you have a nonlinearity associated with the rotations, you integrate that in the explicit way, and then you part of the equations integrate implicitly. So you will end up with so-called explicit implicit method, which is very powerful technique. And then you can have in certain case scenarios some efficiency improvements or leverages, because you further decouple the equations, and then you can solve them faster and faster by exploiting the certain facts about the physics. But that yet to be exploited. And then it's a big word, but which is not investigated. So it's like an unexplored Amazon forest. Yeah, which lots of things to be discovered. And then we don't know even everything about what is possible with that techniques. And that is beautiful if you are a researcher, because it's a whole world to explore. Yeah, and then not many people to investigate that. Everybody investigating AI, for example. It's a cool thing, but it's like crowded space, yeah? It's like going to the Venice in the tourist season. Lots of people there. Nice place, Venice, but lots of tourists. And then mixed elements are exploited. People going from time to time there, but it's like no tourists there. It's a whole thing, whole space to explore, Amazon forest. Yeah, so that's why I will encourage that to look into that things.
Yes. So additionally, what you can play this, change the Young's modulus, Poisson ratio. If you are running the Hooke's beam, I would advise you to change the warp factor. It just changes by how much the warp is shown rather than by how much the warp is. So you can see the whole beam going upwards. And if you are really adventurous, you can do the convergence analysis with changing strains, changing the changing the rotations, changing the stretches, and get similar plots. All the functions should be there. But this one would require slightly more Python knowledge. But regardless, you can do everything just by changing things and view. Do whatever you feel like you're interested in, I guess. Okay, I think that's all for